You should follow your own curiosity and don't worry too much if people around you say, well, that's a silly question. Everyone knows the answer to that. Till I was about 19 or 20 years old, I never thought seriously about becoming a scientist. I mean, we are not a rich family, so I had to find my own means of support for a second degree.
My name is Bin Yi. I study theoretical physics. Professor Leggett is my mentor. We've known for more than 10 years.
Hi.
Hey, yeah.
Hi.
How's it going? Haven't seen you for a long time. This is like five fortune. It's basically wish you all five fortune. So it includes. So the first one I think is longevity.
Yes. Longevity I already have, I guess.
And wealth. Wealth. And then the third one is inner peace, like one reconciled with oneself. I think you all have. And then inner peace and virtue. One wants to get respected from a moral aspect.
Yes.
And then also good ending, which means like one's value, one's legacy gets passed down.
Oh, very well.
Yeah. So we should all five portions.
I see. I have a list of 3 things one should share in order for the marriage to be successful. You should share a sense of basic values, you should share a sense of humour, and you should share an opinion about whether the bedroom window should be open or shut.
So, what's the most attractive parts of Haruko for you, Tony?
He's a very warm person and very original, I think, in a sort of a very peculiar kind of way, but she really is original and exciting.
So, what do you think about him as like as a husband?
To be honest.
I could trust him.
Okay.
So that was very important. And the other one, I told you that he is a good person. Well, he's honest and kind. And those were 2 traits that I liked.
Oh, okay.
Honest, probably moronically.
What is the most memorable thing or events that has occurred? Just one.
Most memorable event that has occurred for me?
Yeah.
Well, I think I'd have to say the birth of my daughter.
And what is the most valuable thing that you've had?
The most valuable thing that happened to me, as it were, was that when I started my career in physics at, my permanent career after the postdoctoral work at the University of Sussex in 1967, my conditions of work, basically my job was teaching.
Okay.
And that if I did a good job teaching throughout the week, I could go home on Friday night and feel I'd earned my salary. And then if I wanted to, I could spend at least part of the weekend doing research. And the university would support me in this. I mean, it would find me secretarial help and libraries and things like that. But research was not part of my job. And I think that was enormously valuable. And had it not been for that, I don't think I would have been able to do the work on superfluid helium-3, which was eventually recognised by the Nobel.
And what is the most proud event?
Again, if you accept family things, I think probably the work I did with my student Amir Caldera and other people on quantum dissipation, that did identify an important problem which had not been addressed or not seriously addressed in the literature. We were able to produce eventually quantitative and fairly definitive results, which I think have stood the test of time. That work was done 1980, 1981, roughly.
And that's not the work that you did with helium-3, because people would generally think that most proud thing would be the work that leads to the Nobel Prize.
Well, yes, that was also I'm also rather proud of. Yes, and I think one reason I'm proud of that is that one reason I was able to do that work is that I knew when this problem came up. I mean, the problem was presented rather starkly and clearly by the experimentalists, by the experimental results on helium-3. It was a puzzle staring you in the face. And when I attacked that problem, I knew what I needed to know. That is, I knew some fairly basic experimental details about helium-3 and some basic theory, also Landau-Fermi liquid theory, and so on and so forth, and the elements of BCS theory, so on. However, equally importantly, I did not know what I needed not to know, and what I needed not to know was the standard theory of NMR, nuclear magnetic resonance. Had I known that, the standard theory, as a lot of my colleagues did, I would have probably chased off in completely the wrong direction. Okay. But because I didn't know, I just did take the problem from scratch and using some rules and so forth, which other people basically hadn't thought of, and that did work out.
Is that partially luck?
Well, yeah. I mean, I obviously was very lucky in many ways. Yeah. Until I was about 19 or 20 years old, I never thought seriously about becoming a scientist. And in fact, my my high school education and my university degree, my first university degree, had nothing to do with science. In the high school, I specialised in what was then regarded, we're talking here about the late 40s, early 50s. In those days, the most highly regarded educational option was regarded as the classics, Latin and Greek literature, and so forth. And so I specialised in that during my high school education. And when I went to Oxford as an undergraduate, I took the Greats degree, which is well, you do the first. It's a 4 years, so 12 trimester course, and for the first 5 trimesters you study classical, that is Greek and Latin, languages and literature, and for the remaining 7 you study a mix of ancient history, again ancient being Greek and Roman, so a mix of that and philosophy. And that's what I did my first undergraduate degree. And it was only towards the end of my first undergraduate degree that I thought about doing anything else, really.
So how you transit from literature to physics after your first degree?
Yeah, with great difficulty, actually. First of all, I had to convince some university to accept me for a second undergraduate degree. And very luckily, my Oxford college was willing to accept me, although in the end that's not where I went, but they would have accepted me. I guess they knew something about me at least. I mean, they knew how I performed in the Greats degree. The second problem was to find some means of support. I mean, we are not a rich family, so I had to find my own means of support for a second degree. Turned out there was another college in Oxford, Merton, And they had a special scholarship, which they was normally given for people to do a graduate degree. But in my case, they decided to make an exception and offer it to me for for a second undergraduate degree. And so that's what they did. There were actually the original scholarship was funded by an alumnus of the college way back sometime in the middle of the 19th century, I think. And of course, in those days, political correctness was not what it is today. So, so he had specified that the holder of this scholarship should be an Anglo-Saxon Protestant. That didn't fit me because I'm partly Irish and certainly not a Protestant. I was brought up as a Catholic. Fortunately, the college had foreseen this problem, this kind of problem. They tried to get the terms of the scholarship changed, but it turned out that was impossible. It was sort of legally solid. So they'd actually decided that they didn't want to waste the money, but at the same time, they obviously couldn't live with this very politically incorrect condition. So what they said is, well, if we get a candidate who satisfies these conditions, that is, he is an Anglo-Saxon Protestant, then we will use this money for a scholarship to him. If, on the other hand, we get a candidate who otherwise qualifies but does not satisfy these conditions, then we'll put up a sum of our own money to instead. And so that's what they did with me. That so-called Nobel scholarship. What's ironical is that I think nowadays many of the holders of this of the original Harmsworth, so-called Harmsworth scholarship, are indeed Anglo-Saxon Protestants, but they're women, because in the mid-19th century, the donor had never thought it was even necessary to specify that the holder should be male. Anyway, so that's quite amusing, I think. Anyway, so that was the second difficulty. The third and most serious difficulty was the military draft, because it was known. I had postponed the military draft when I entered Oxford for my first undergraduate degree. That was quite normal, but the expectation was that I would do it at the end of after my first degree. However, it was known that 1959, which was the year when I graduated from my first degree, that was the last year of the military draft in the UK. Okay. And so if I were to defer it further, that meant I would get out of the draft altogether. And so they looked so the draft board looked very sceptically at anyone trying to postpone further, as it were. So I have to go up to my draft board and say, look, you guys, you've given me 4 years of extension. I would really like another 2 years in order to do a second degree in physics. And they would obviously look at me and say, oh, we've got your number, and we know you just want to get out of it altogether. So that didn't look very promising. It looked like I was going to have to do the draft, which would have been a serious obstacle to me continuing in a physics career. But very luckily, in October of 1957, the former Soviet Union had put up the first Sputnik, the first Earth satellite. And everyone in the world could see this thing going pop, pop, pop across the sky, and everyone in the world knew that this had not been done by the so-called leading technological powers, the US and the UK, but rather by the Soviet Union. And so immediately this huge outcry from all the pundits and opinion makers and so on. How come that the Soviet Union has managed to get ahead of us in this incredibly important technological field? And they soon came up with the answer. The answer was that, well, because we've encouraged all our best and brightest people to go into useless subjects like classics rather than useful subjects like physics. And so immediately there was this move to encourage people who had been doing these liberal arts topics to switch into hard science topics. And I was able to sort of ride the crest of that wave. I was not the only one, by any means. There were a number of people who, for example, had done their undergraduate degrees in history and tried to switch into chemistry and so forth. As far as I know, I don't know any of those people who really succeeded in doing that. I guess perhaps the way of thinking of chemistry is not somehow consistent with what they've done in physics. Whereas for me, it was. It wasn't totally natural, but it wasn't completely alien either. I could use some of the techniques that I'd learned in the philosophy part of my course, for example, in the context of physics.
I see. That's a very interesting experience you had.
Yeah, I think had it not been for that burst of adrenaline, I probably would have quit academic physics and I'd gone into high school teaching or something like that.
So do you have a suggestion, advice to young students?
You should follow your own curiosity and don't worry too much if people around you say, well, that's a silly question. Everyone knows the answer to that. I always give people the example of Einstein asking the question, the following question. Since the time of Galileo, which was 300 years earlier, people had taken it for granted that all bodies, no matter what their composition or their shape or size, in vacuum, in the Earth's gravitational field, they always fall at the same rate. So people just sort of taken it for granted. Einstein asked why. I'm sure when Einstein first asked that question, a whole lot of his colleagues just sort of patted his shoulder and say, well, that's a silly question. We know they just knew, But by thinking hard about that question, Einstein eventually evolved the theory of general relativity, which is, I think, the most beautiful part of modern physics. So as I say, just follow your curiosity. And secondly, don't worry too much about whether the question you're asking has been answered in the literature. Try to approach it from scratch and try to answer it your own way. If at the end of the day you come out with an answer and you then go back to the literature, you may find it's been answered, but you'll have discovered something by doing that. The time will not have been wasted. Thirdly, don't throw away anything, any honestly done piece of research as being a waste of time, even if it didn't pan out for the problem you're actually looking at. Just put it away in a drawer. Write it up properly. Take care to write up what you did properly. Put it away in a drawer, and the odds are that in 10 or 15 years, it'll come back and help you out in a way that you never expected. This happened to me with the work I did in Kyoto on two-band superconductors. That turned out to be the clue to getting a proper microscopic dynamics of helium-3 in the end. I could never have dreamt that when I first did the work. Fourthly, keep things simple. Don't do more than you absolutely have to in terms of high-powered techniques like Green's functions or functional integrals or things like that. which are really not very intuitive, and try to always formulate things in terms of direct, simple physical concepts if you possibly can. And finally, if your job is one which requires you to do both research and teaching, then take your teaching at least as seriously as you take your research, if not more seriously. You'll find that not only is that good for your students, but it's good for you too. Some of my best ideas during my research career have come out of my teaching work, in fact. So it's certainly not a waste of time to spend time and effort on your teaching activity.
So I wonder, how's your experience with John Barting? You did your postdoc with John Barting?
No, no, I did my postdoc with David Pines, but it was John Bardeen and Leo Kazanov who suggested to me the problem which actually triggered my work in my postdoctoral year on superfluid helium-3. They actually suggested to me to work on the spin diffusion, how the spin diffusion coefficient would change if liquid helium-3 were to become superfluid. And I started working on that, but then I got sidetracked into this question of how to put together BCS theory of superconductivity and Landau-Fermi liquid theory. And that's what I ended up working on, and I never got around to working on the spin diffusion coefficient.
So were you working with John Barting or?
No. I mean, I really wasn't working with anyone. I was technically a postdoc of David Pines, but he really basically let me do what I wanted. I was very appreciative of that, actually.
Yeah, so that's that's how you supervised me as well.
Oh yeah, well, right. I mean, I think it is fruitful to do it, people.
So apparently a lot of programs where students they are like within a set program where they are told to do like step by step. They have like step by step instructions. So what do you think about these two different styles, like a freestyle or like a?
Well, I mean, yes, that's of course not an accident that a lot of postdoc programs operate in the way you say, because they're often funded by some kind of agency which has given the money for a particular purpose, and so they don't like people to deviate from that very much. But luckily, David Pines, I forget which grant I was on, it probably was a National Science Foundation grant, I think, that was not very restrictive, and so David Pines could afford to let me just basically do what I wanted to do. And he was pretty supportive of me. Anyway, as I say, I did know John Bardeen pretty well, but he was a difficult person to talk to. I would often come up, just run across him in the corridor, and there would be some question that I would want to ask him. So I would sort of stop him and ask the question. And he, for a long time, he just would do nothing. He would just stand there and say nothing and do nothing. And at times I really began to wonder whether I'd got the wrong ear, because he was sort of deaf in one ear and you had to address him from the right side. And so I began to wonder whether I'd got the wrong ear, as it were. So after about a minute, a big smile would come across his face, okay, and he would give you an answer, a sentence, which was just basically a few words. And so then you had to think about that and try to ask him another question, and again you had to wait a minute or so for the answer. And it's very peculiar. During the last few years of his life, he had a theory about charge density waves. It was very different from the standard I mean, there was a standard theory by that time of charge density wave conductivity and so forth. John Bodine had a different theory, and he repeatedly tried to explain it, and almost no one could understand it, and that included me. I must have, quite literally, I think I must have spent days of my life just listening to John Bodine explain this theory, and so he would talk for 15 minutes or so, and then he'd stop and I'd say, okay, John, let me try to summarise for myself what I think you're saying. If I get it right, you said ... and then he'd say, no, that's not it. And talk again for another 10 minutes or so. So, quite unfortunately, quite literally, to the end of his life, I never really understood what he meant with that thing. And as I don't think anyone else did. But there was one person who claimed to understand it, which was John Tucker, who was an experimentalist, also working here at the U of I.
Is he still here?
Sorry?
Is he still here?
Well, no, he unfortunately died quite some time ago now.
Okay.
But he, so for a period, he actually collaborated with John Bodine and tried to demonstrate experimentally that his ideas were right. But in the end, that didn't work out, and they had some kind of falling out, and so they no longer worked together. And then sort of reasonably soon thereafter, John, I forget what was the cause of his death, but it was sort of fairly sudden and I think unexpected. And that's John Tucker. So he died first and then later, John Bodine. When, of course, I went, needless to say, to the memorial service for John Bodine. And what was amusing was that he noted a few things which he hoped would be mentioned in his memorial service, and he'd sort of just mentioned briefly the 2 Nobel Prizes he got. But then the thing he really wanted to mention was that he was a very keen golfer, and he once achieved a hole-in-one. Do you know what a hole-in-one is?
Like a hole-in-one is like I just do one.
Well, it means normally on a normal golf course, you try to get the ball into a hole, and you normally take 3 or 4 attempts. So you'd first of all hit the ball close to the hole, and then you'd have to hit it closer, and eventually.
So just one hit.
Yeah, but he got it in one, yes, and he was more proud of that than he was of his 2 Nobel Prizes. He's a very kind person, though. He really helped us get established here when we first came.
So I'm just wondering from the parents' side, if their kids wants to go into science, become scientists, do you have any suggestion for them? Like how like from a parent's perspective, how to support a student in this case, for young student?
Well, in my case, as I think perhaps I mentioned yesterday, my father was actually a science school teacher, but he never tried to persuade me to go into science. In fact, as I told you, I didn't at high school. If anything, I think the classes I took with him might have put me off physics rather than encouraged me. I think probably the most important thing is to, if your child is interested in physics, say, or science more generally, make sure that they have a high school teacher who is imaginative and encourages them. it's very easy for people, for people to get put off by the high school classes they take in science. And so it's very important they're not. It's important that they have an imaginative high school teacher. And you might even, if you are a parent and your child wants to go into science, even make that a factor in choosing school, I think. Give them, make sure they have time to explore their own interests.
Yeah, so I think that would be hard sometimes. Like when in China, I know, like the students get very overwhelmed with coursework.
Yeah, I mean, I realise that.
So
Yes.
to find a balance, maybe.
Yeah, and I mean yeah, I mean, this is bad enough in the US, but in China it's worse, I agree. Yeah, and in fact, I mean, as you no doubt have experienced it, if you're not lucky enough to get in a sort of reasonably flexible group, you may have to spend all your time working on a subject which really rather bores you. And worse, I think people have to continually worry about producing papers which will get them the next job. And I really think that's a terrible feature of the system. The one thing that you, I think, really don't want at the sort of stage which you are now and which I was at, say, when I was doing work at Sussex, what you don't want is to have to produce a paper for some high impact journal in a time of whatever you have, 2 to 3 years before you have to get your next job. That's a way to kill any real imaginative research, I think. Sure, people do perform okay under these conditions, but it really isn't a good thing.
Well, okay. So what is a good thing then? Just one follows one's curiosity.
Well, okay.
And it may take a long time.
Look, I mean, I was lucky, and if I could do it, I would reproduce the conditions. I think I talked about this yesterday. If I'd reproduce the conditions which I had when I first went to the University of Sussex in 1967, I guess. And the conditions were that basically my job, as I saw it at least, my job was teaching. And if I did perform my teaching job conscientiously throughout the week, then on Friday evening I would go home and think I'd earned my salary. If I wanted to spend some time doing research in the evenings or weekends, well, I could do it. The university would encourage it and they'd support me in doing it, but it was not part of my job. I did not have to produce research as a part of my job. That I think was marvellous. That's what gave me the freedom to take my time and explore the problems I was looking at, in particularly the problem of the helium-3, and not feel rushed about it. So you see, between my first paper on helium-3, that was in, I think, September of 1972. I always get the years mixed up, I think it was 72. So that was in the fall of 72. There was a period of about 9 months when I didn't really produce anything. I mean, I was thinking about it a bit, but I didn't really produce anything until I went to Cornell in the spring of 73. Then I had another burst of activity. I was able to produce a microscopic theory. But between those two papers, I was really spending most of my time on teaching. And it didn't matter. It didn't matter from my point of view, my personal career. That was marvellous, I think. Very few people these days have that kind of opportunity.
Yeah, sure.
I mean, I think when people ask me, how do we get those conditions? The only way which at least approximately gets one towards those conditions is to go into teaching at a liberal arts college, like say Parkland here or like. Now you see, if you look at the field of quantum information, and you look at some of the people. I mean, nowadays we're quite well into it, so this doesn't quite apply so much. But if you looked at the field of quantum information, let's say in, I don't know, 1990, 2000 and so, who were the leading figures in it? The leading figures in it were almost always people who had not worked most of their careers at major research universities. They become interested in the foundations of quantum mechanics and related things, and they deliberately got off and taken jobs at these small liberal arts colleges in the middle of nowhere. Like say Williams College in Massachusetts, where my daughter spent a year. Like say Hamilton College in upper New York State. This meant, because they had a heavy teaching level, sure, but no heavier than I had at Sussex. They, in fact, probably lighter than I had at Sussex. They had adequate library facilities, they had secretarial facilities and so forth. So at least if they were theorists, they had what they really needed to carry out a research program. And they could do it in the evenings and the vacations and so forth. And many of them did. So as if people like Philip Pearl, for example, who was a big name. I mean, I think he's now well past retirement, but he was a big name in the quantum foundations field in the 80s and 90s. And so he'd deliberately given up the prospect of working at a major research university and gone off and worked at these liberal arts colleges. Now, I don't know whether anything corresponding to that possibility exists in China, but he does, and I'll say go for it.
Oh, well, I was actually thinking about it too.
Yeah.
I had an experience after I graduated from college. I went to work as a high school teacher, and I tried to.
Oh, yes, of course, I remember you did, didn't you? Yes, right.
And I tried to.
Yes, right. Well, as you say, well, yes, if you can't go to a liberal arts college, then a high school is certainly next.
I think it was a fun experience, I would say.
Yes. Yeah, but you probably didn't have quite the library facilities and so forth that you need for a serious research career. You know, so I don't know. It does depend on the immediate circumstances, but certainly that's what I tell people. Tell people who want to stay here in the US. I mean, unfortunately, a lot of people seem to take the view that a heavy teaching load is, as it were, the kiss of death. That's not true. I mean, when I was at Sussex, if you don't even count graduate teaching, you just count undergraduate teaching, tutorials, lectures, ... I was doing anything from 12 to 15 hours a week. And that's probably more heavier than even at a liberal arts college, let alone at a major research university here. Yes.